Okay, so we have a compressor and we have air, which we're going to assume as an ideal gas. It will flow into the compressor at this temperature and this pressure, and is going to go through an area of 0.030 meters squared with a volumetric flow rate of 4.5 meters cubed per second. It's going to enter the compressor, and obviously it's going to get compressed, and it's going to increase its speed to decrease its speed to 17 meters per second. The pressure will go up to 2.4 bars, and the temperature will go up to 400 K. We don't know the exiting area if it's lower or higher. I just generally assume that it looks like that. And we are not even asked for the area, but we may need it. We need the original velocity. We don't have that. We want the mass flow rate. We don't have it. And we want the power input. So these two things we can get from the continuity equation, meaning the conservation of mass. This power input, that's basically work. And we're going to have to employ the first law, open system, steady state for compressor to get that. So let's just worry about these first two things first. And in order for us to get the mass flow rate, what we could do is recognize that the mass flow rate is going to be equal to the density times the volumetric flow rate. Okay, so that's going to be true for us because density is kilogram, let's say, per meters cubed, and volumetric flow rate is going to be, say, meters cubed per second. The meters cubed will cancel, and I will be left with kilograms per second. So I want something that looks like I want to be able to get my density. I don't have the density in the beginning or at the end. And so I know the volumetric flow rate here. What I should strive to do is get the original density. Because if I can get the original density, I have the original volumetric flow rate, and I can get the mass flow rate, which is going to be true throughout. Okay, so how do I do that? Well, to remind you, and since this is an ideal gas, we can get the density directly from the ideal gas equation. So if we look at PV is equal to nRT, okay, and we want to get kilograms per meters cubed to get this to be kilograms per second. I know the pressure for the first state, I know the temperature for the first state. I don't know V or N, but that's okay because I can solve for N over V, which is going to be moles per meters cubed, those, assuming it's SI. Then I can convert moles to kilograms using the molecular weight, or moles to grams, and then grams to kilograms using the molecular weight, and I'll get kilograms per meters cubed. So that's my goal. That's my idea here. So I know for my first state, I have 1 bar for the pressure, and I'm going to solve for N over V when I assume it's one variable. We're going to solve for that thing. And then R, I'll get back to in a second. I know that the temperature at first is 295 K. So I'm going to go select an R that's got bars and Kelvin in it and meters cubed in it. And if you look at your R chart, this one will be just fine. 8.314 times 10 to the minus fifth. This is going to be bar meter cubed divided by mole Kelvin. Meaning, so when I solve this for N over V, I will get this to be moles and this to be meters cubed. And indeed, I do. So when you solve for N over V, you get that N over V is 40.77 moles per meters cubed. Okay. So what can I do with that? Well, I need to make that into kilograms per meters cubed. Not a problem. I will convert moles to grams and then grams to moles. So I'm after rho. So I have 4.77 moles of air divided by meters cubed. And then I know the molecular weight for air, and it's in the back of the book, you don't have to memorize it, is 29 grams per mole. And I want to cancel out mole. And I know it's 29, about 29 is 28.9 or something like that. 29 grams of air is going to be 1 mole of air. So that cancels out my mole, which I don't really want. And then I can then say it's 1,000 grams per 1 kilogram, get rid of my grams, and I eventually get that my density, my initial density, is 1.182 kilograms per meters cubed. Okay, so then if I go back to well, I don't actually, I erased it. So what we said, we could do this right now, is that the mass flow rate, as we said, is rho times the volumetric flow rate, okay, V dot. And since this is going to be meters cubed per second, this is going to be kilograms per meters cubed. The meters cubed will cancel out, get kilograms per second. So I can get my mass flow rate that way. My volumetric flow rate was given to me in the beginning of the question, and it was 4.5 meters cubed per second. So I'm going to use that directly. So I know that my density is 1.182 kilograms per meters cubed, and times that by the volumetric flow rate of 4.5 meters cubed per second. And when I do that, I get my mass flow rate, which is 5.32 kilograms per second. Okay. And this, if you will notice, I did not call that. So this was rho 1 and the volumetric flow rate 1. It's not going to be M1 dot because M dot is constant throughout. There's not going to be, there's going to be a one M dot for everything. So it's going to be 5.32 kilograms per second coming in here and coming out there. Okay, mass does not disappear. Okay, so I'm going to erase all of the stuff here, and I know my mass flow rate now, which is great. So my mass flow rate now, which is at I think throughout the entire thing, is 5.32 kilograms per second, and that takes care of that. Now I want the initial velocity, and I want the power that goes through it, which is just the work. Okay, so I'm going to go for the velocity, and it's again going to be a continuity equation type thing. And I know that rho 1, vel 1, A1 is going to be rho 2, vel 2, A2. Okay, so I'm going to mark in red what I know here. This is the continuity equation, assuming that it's going to be the velocity does not change with area, which we can assume for most questions unless otherwise specified. So that's fine. So I know the outgoing velocity. I know the initial density, and I don't know my initial velocity. That's what I really want. That's what we're after. I know my initial area. That's given to me right there. And I don't know this either, and I don't know this either. So what can I do? Well, to get rho 2, we were able to get rho 1 using the ideal gas equation. We could get rho 2 using the same exact thing. So let's do it again. So to get rho 2, again, it's going to be very similar. Let's do it. We're going to apply the ideal gas law. P is going to be N over V. We're going to solve for N over V times RT. Again, I'm going to solve for N over V. It's going to be moles per meters cubed. Then I'm going to convert moles to kilograms, and I'm going to get kilograms per meters cubed, which is going to be my second density. So I'm going to use P2, and this is going to be 2 and 2. Okay, so using our final state variables, I know that this is the pressure 2 is 2.4 bars. This is going to be N over V 2. Again, it's going to be the same R as before. and the temperature is 400 K. Yeah. And so when you solve for N over V2, for state 2, let me see, you get 72.17 moles per meters cubed. Okay, again, I don't want that. I want kilograms per meters cubed, but I can convert, no problem. So what I'm going to do now is the same as before, 72.17 mole per meters cubed. I know that my molecular weight for air is 29 grams of air per 1 mole of air. And then I don't want grams, I want kilograms. So it's 1,000 grams per 1 kilogram. And I get 2.093 kilograms per meters cubed. So now I have both densities. I didn't record the other one. I'll just put that in right now. So I know from my thing from before, I just forgot to write it down, that my initial density is 1.182 kilograms per meters cubed. And I know that my final density, rho 2, I just calculated a second ago, it goes up to 2.093 kilograms per meters cubed. Okay, so now I have both densities. Great. So again, let's just show again what we have and what we don't have. For the continuity equation, rho 1, vel 1, we want vel 1, A1, rho 2, vel 2, A2. So now we have both rows. We have the initial area. We have the final velocity. We don't yet have A2, and we can't just assume the area stays the same. It very much does not. So we have to calculate area 2. Well, how will we do that? We know that the mass flow rate by itself, the definition of the mass flow rate is rho vel A. Okay, so I can just use the second state and get the area because I know the mass flow rate. The mass flow rate is 5.32. So this is going to be 5.32 kilograms per second. This is going to be 2.093 kilograms per meters cubed. This velocity is 70 meters per second. And then I can calculate my final area, which will be in meters squared. So when you punch that into the calculator, you get that the second area goes from 0.03 to now 0.036. So we actually increased in area, 363, we'll say, meters squared. Okay, so now I'm going to go back here and I'm going to write that as one of our givens here. The final area is 0.0363 meters squared. Cool. So now we can just use everything that we have to find the final velocity. So if you look at this equation, and now we also have A2. So that means that we can just punch everything in here. I have 1.182 kilograms per meters cubed, and that's my initial density. My velocity 1, well, that's what I want. My initial area is 0.03 meters squared. That's going to be equal to rho 2. We just calculated that. That's 2.093 kilograms per meters cubed. Velocity 2 is 70 meters per second. Okay. And my final area is 0.0363. You will notice I didn't really need to do this way, but it's just one way of doing it. Okay, so 2.0, so I'm going to punch that into the calculator. and we get that our initial velocity, oops, can't see it, is 150 meters per second. So our initial velocity is 150 meters per second. Okay, so that now we have the mass flow rate and we have the initial velocity. Okay, cool. So I'm going to transcribe that there. So we have it. My initial velocity is 150 in case we need it. Vel1 is 150 meters per second. Okay, that's part of the givens and all the setups. Okay, now we need the work required to run this entire steady state thing. So if you remember, for this particular steady state device, we can assume that there's going to be no change in height. And so that cancels itself out. We can assume it's a steady state condition. And so the first law of thermodynamics, open systems, boils down to this. I mean, it's complicated enough, I suppose. Q minus W dot is going to be M dot times the change in specific enthalpy plus M dot, and then the change in kinetic energy. Okay, Vel1 squared over 2. Let's see what we have and what we don't have, what we need to do. So we're looking for W. That's what we want. We don't have that guy. We have Q. We're given that specifically. We calculated M dot. That's right above the check mark. We don't have the specific enthalpy. Again, we have the M dot, and we have both velocities. We just calculated it. See why we would need them in addition to just getting the continuity. We also need them to get the work for this device if we're trying to make this device work, if we're trying to run the compressor. Okay, so now that we know what we need, we're trying to look for the work, and we got everything except for the specific enthalpy. So the specific enthalpy, that's for an ideal gas. The specific enthalpy is going to be the integral of the specific heat, constant pressure, dt, from T1 to T2. Okay, so I'm going to take a bit of a longer route. I don't have an average CP given to me, so I'm going to have to integrate it. So I'm going to go to the back of the book to try to find my CP, and let me show you where I got that data. You could do it yourself. Let's see, pull up the chart. Okay, so I have this right here. Let's see, I have CP over R is going to be equal to A plus BT plus CT squared plus DTQ plus ET to the fourth, like that. And I'm just going to go to air. I'm assuming it's going to be, you can't see it that well. It says here air in parentheses dry, and it's a bunch of numbers here. The number for the A, a number for the B, a number for the C, etc. So I'm just going to do A and B because these C, D, and E are tiny. So I'm just going to truncate that at B. I could probably get away with truncating it at A, but I'm just going to truncate it at B. And if I transcribe that, let me show you what you get. Okay, so what I get, so from the back of the book, you're going to get, let me just show you kind of what ends up happening. You're going to get CP over R. I got that. And if I go to the back of the book, CP over R is 3.653 minus 1.334 times 10 to the minus 3 T plus 3.291 times 10 to the minus 6 T squared. And if I solve all of this for the CP that I want, it will be in joules per mole Kelvin if I isolate my CP. But you see, it's given to me in CP over R. I don't want CP over R, so I got to multiply through by R to get CP. So it's going to be this times R, this times R, and this times R, like that. And I'm just going to integrate that with respect to temperature to satisfy that integral right above it. So that's what I'm going to do. And I start with a temperature of 295 Kelvin to a temperature of 400 Kelvin. And I'll just basically write that in here. So I'm going to get 3.653 R minus 1.334 times 10 to the minus 3 times R times T plus 3.291 times 10 to the minus 6 R T squared. And this entire thing is dt. Now, why did I truncate that when they were giving me additional terms? So this was A, B, C, and then I said the heck with D and E. D was some number times 10 to the minus 9th, and E was some number times 10 to the minus 12th. So I figured they probably wouldn't change much for it. Is this, by the way, the definitive R? Sorry, CP? No. It's just an empirical relation. It's got no grounding in any sort of theory. It's just what people observed and put that into an equation. So this is not a law or anything like that, just some observed values. Okay, so when I integrate this, and you probably will use like Wolfram Alpha or something, but you don't have to. I use my TI-89 to just punch the numbers afterwards. But if you just integrate it, so I just set it up after the integration, and then I put that into my TI 89, 1.334 times 10. And you could use the TI 89 to just run the entire thing. I just was being extra studious, I guess. Like this, 3.291 times 10 to the minus 6 RT cubed over 3. Okay, and this entire thing is evaluated from 295 to 400. And that's what I did. I just put this into the calculator. So this times 400. R for our case to make everything work should be 8.314 joule per mole Kelvin. And then when we do all of this, we're going to get delta H in terms of joules per mole. So I did all that. I punched all that in, and what I got was that my delta H, my change in my specific enthalpy is 3,133.8 joules per mole. Okay, so that's cool. So let me just. Okay, now with this delta H, which is in per mole basis, we can apply the first law of thermodynamics to try to find the amount of work that's required to operate this compressor. So the first law for this particular device, this assumes that there's no change in height, and we can get from the first law for this as m dot delta H plus m dot times the change in kinetic energy, vel2 squared over 2 minus vel1 squared over 2. And what I suggest we do, I think easiest when we deal with the first law with the metric system, is to keep everything in SI. So everything should be in kilograms, meters, seconds, etc. Okay, so we have a mole here. And ordinarily, it will be okay to use if our flow rate here was in a mole flow rate, but we have that in kilogram basis. So we need to convert this to joules per kilogram. Okay, and once we do that, we pretty much have everything else. So let me just do that really quick. Delta H is 3133.8 joules per mole, and I know that for air, 1 mole is 29 grams. And I also know, now it's going to be joules per gram, you want joules per kilogram, the SI unit for mass is kilograms. So, so we know to cancel grams that we need to multiply this by 1,000 grams per kilogram. And this will give us the delta H that we actually want. Let me just get that real quick. So there's 3133.8. And this is going to be 108.62 joules per kilogram. Okay, so I'm going to write that here because we don't need that in moles anymore. We want the delta H in kilogram basis. So 108.62 joules per kilogram. Okay, so now we should have everything for the first law, and almost everything is in the correct units. So the Q dot is in kilojoules per minute, and we want in joules per second. So let me do that quick as well. Q dot 900 kilojoule per minute. Hopefully we know that 1 minute is 60 seconds. And we know that 1 kilojoule is 1,000 joules. So, oh, this is negative. So then Q dot ends up being negative 15,000 joules per second. So I'm going to correct it up here so we don't get that confused. And then we're going to use, I think everything else is in SI, 15,000 joules per second. Okay, so now I'm ready to put everything together. So this Q dot here is negative 15,000 joules per second minus work dot. This is in kilogram per second, so that's cool. So 5.32 kilograms per second. And I can actually put all that stuff together because I can factor that out. Delta H will be 108.62 joules per kilogram. And again, it's kilogram because of the kilogram, joules per second is good. Plus vel squared, the final velocity squared, and then the initial velocity squared, both divided by 2. And the final velocity is 70, and the initial velocity is 150. And it is in SI, it's in meters per second. So plus 70 meters per second squared over 2 minus 150 meters per second squared over 2. And then all we got to do is isolate this work term. Let's get that up here. And when we do, we get that work is negative 543,074 joules per second, or this is really watts, right? And that means that we need to input about 500,000 watts to make this compressor work.